what hopefully is a memorable event. So welcome to everyone, which we hope is a memorable event. I'd like to welcome you all on behalf of our NetworkPlus in Digitalised Surface Manufacturing. And the purpose of our NetworkPlus was initially to bring together UK academics in the area of digitalisation of surface manufacturing. But we're very pleased to have widened the net to include worldwide experts in this field. And we had the idea to start a series of events to improve the understanding of different kinds of coating methods. And this one is the first, and this is what we're calling Spray Week. And I should really thank Swaraj for driving this forward, and together with Pamela's help in arranging it. I ought to say to you that the DSM, Digitalised Surface Manufacturing NetworkPlus, involves 5 universities in the UK, Manchester, Sheffield, Queen's University Belfast, London South Bank University and Cranfield University. And gradually we are widening the number of UK universities involved, and then also, as you can tell now, worldwide universities that are known to be real centres of excellence. So Pamela's put the programme up there, and the first speaker is Christian Morrow from Concordia University in Canada. And Christian, you're going to talk about monitoring and control of thermal spray processes, opportunities and challenges. Before I pass over to Christian, Swaraj, would you like to say a few words?
Yes, Alan, definitely. So on the note, first of all, welcome everyone. And it is greatly pleasant to see worldwide expertise of thermal spray through this event that EPSRC DSM is very proud to actually bring to all of you, whichever part of the world you are in. And we have this whole week dedicated to thermal spray, and it's a great opportunity to learn from some of the best that we have kind of, as an ECR, learned from by reading their books, their notes, their lectures, and so on. So it is hoped that many ECRs across the world, ECR, by the way, stands for Early Career Researchers, or ECI, Early Career Investigators, would particularly take advantage to make networks to ask questions and get direct clarifications on any of the challenges you have experienced in this field. And in the spirit of this particular event, we have also organized a specially dedicated issue on thermal spray manufacturing. So right now, the journal Frontiers in Manufacturing Technology has already put up a web page with an open invitation that is being shown by my colleague Pamela on the screen. So there's a research topic on thermal spray manufacturing processes, which is a dedicated issue for celebrating the success of thermal spray that we are editing through DSM NetworkPlus. So those who would like to submit their publication on any aspects of thermal spray, they are very much welcome to do so with the deadline of 24th of June that we have kept in mind. This particular dedicated issue will also display some of the golden contribution articles as keynote contributions from our esteemed speakers who are going to talk to us over the next 4 days. And one of the dedicated day, which is the last day of this week, has been kept purposely designed in such a way that it will be talked, or it will be contributed by ECRs from India, US, and LSPU in the UK. So it's going to be an exciting week ahead, and it's my great pleasure to start the first day of this week from the very west part of the world. So we have basically designed this to accommodate the various time zones that we have between the UK and other countries. So what we have done is today's talks are going to be from the west part of the world. So we have one speaker from Canada, another from the US. Tomorrow's day is going to be led by the east side. So it will be particularly from Australian and Indian colleagues. And we then have a day after tomorrow dedicated to Europe. So we have an eminent speaker from European continent per se. So without any further ado, let me invite Professor Christian Morrow with the kind introduction with his permission. I'd like to say a few words to introduce him. So Professor Kishan Murray as such needs no introduction. He, as an ex-editor-in-chief of Journal of Thermal Spray Technology, is very well known to the community, but he's always a very kind figure to begin with, and has been very much of a positive contributor to guide the design of this event. And we are greatly thankful to him in supporting us to have this event, beside many other speakers who are also supporting. So he is a professor in the Mechanical, Industrial and Aerospace Engineering Department at Concordia University in Canada since 2013. And he's also holder of the Canada Research Chair Tier 1 in Thermal Sprayer Manufacturing and director of the Concordia Institute for Aerospace Design and Innovation, called as CRD. Since 2017, he leads the NSERC Canada Research Strategic Network on Surface Engineering for Advanced Manufacturing, which is quite analogous to what we have as DSM in the UK. They call it in Canada as Green Theme, which is a center of excellence recognized all over the world in this area. He's also director and co-founder on the Concordia Research Center on Thermal Spray and Surface Engineering, called as TSSE. And he has developed several sensors for monitoring thermal spray particles in flight and upon impact on a substrate. And the patented optical diagnostic systems, DPV, Evolution, and AccuraSpray, which are very well-known tools for monitoring of thermal spray, are commercialized worldwide for advanced control of thermal spray processes in both production and research environment. His research interests are in the treatment of materials by thermal spraying with any of its variant, and to study the structure property relationships, including diagnostics, modeling, and control. And his research is currently focusing on nano and microstructure coatings deposited by suspension, plasma spraying, and cold spraying for industrial applications. So with that short introduction, I would like to invite Professor Murray to give us the flavor of the inaugural day of thermal spray. Thanks, Christian.
Thank you very much, Saurav and Alan, for the invitation to participate in this unique event. I'm very glad to be part of it. Do you see my screen now?
Yep.
You see the full screen?
Yes.
Okay. Just a moment. Okay. Today I want to speak about some of the past history about process monitoring and control, and what are the opportunities, challenges, and opportunities that we see in front of us at this point. So the outlook of my presentation, I will start with an introduction, speaking about a few challenges that are associated with the control of thermal spray processes, and also some gaps to address, or opportunities for improvement, I would say, and for research directions, and finally a conclusion. Before, I would like to say a few words about Concordia. Concordia is a relatively recent university, founded in 1974, less than 50 years ago. We are located downtown Montreal, and it's quite unique location for the university. Is very fine. In Montreal, we have 5 universities close to Montreal downtown, which is very rich for students. The engineering faculty at Concordia expanding very rapidly, and it's a very nice working place, I would say, in terms of environment. Our thermal spray lab is located on the 4th floor because we are downtown. A dust collector on the main boulevard in the city does not work, so we have to be close to the roof. And we have a quite unique facility at that level. I think we can say that we have the highest thermal spray lab in the world. And now we have the research center involving 11 faculty members, external collaborators, and more than 30 students working full-time in the thermal spray in our labs in the research center. Before starting, I just wanted to give a short introduction to thermal spray. Maybe most of you are well familiar with these processes, but just in case, for those that might be less familiar. I would say thermal spray process is really a family of processes in which I will put my laser pointer, in which you have the feedstock material that might be on the powder form or wire form. And that material here is actually melted and sprayed at high speed using a heat source, oftentimes a plasma jet or combustion flame, forming here molten droplets or semi-molten, in some cases in solid state also, but these particles impinge on the substrate at high speed where they flatten, solidify, and form a coating, a little bit like icing rain. Here, in terms of the size of the droplet, typically it's the range of 20 to 80 microns, roughly. So you have a torch that you scan in front of the substrate for as many passages that we need to get the thickness that are actually targeted. It's an example here of plasma spray, and today I will give different examples related to plasma spray, because it's quite extensively used process, but one of the most complicated to control actually. So in that case, you have the cathode and the anode that are water cooled, and the electrons travel from the tip of the cathode up to the anode surface, forming a high intensity arc, a few hundred amps and a relatively low voltage, heating the gas at a temperature above 10,000 degrees Celsius. So in the forming actually a plasma. And that high speed, 1000 meters per second, high temperature plasma, you inject particles in that flame, and the particles are actually melted or partially melted, heated, and accelerated by the plasma jet, and the particle impact on the substrate, forming a coating. I would say this is an example here of a molybdenum coating, but you see a typical lamellar structure in the coatings, typical interface between lamellae and cracks, etc., and pores, And the coating characteristics, I would say, depends on the particle condition, substrate condition. We'll discuss that during this presentation, but each particle has its own thermal and dynamic history. They are all not the same size, and the injection angle is not the same, and the plasma is fluctuating also. So the thermal history of each one is different, and the challenge is to try to control a chaotic process like that to get good coatings. Example here of this is the same molybdenum coating that we have seen previously, and here's the yttria stabilized zirconia coating. This is the material that mostly sprayed worldwide, mostly for thermal barrier coating application. Again, in a coating cross-section like that one, we see clearly the interface between the splats, the lamellae, we call them splats, and you have pores also. All these features are extremely important actually to have a good, highly performing yttria stabilized zirconia thermal barrier coating system. Those interfaces reduce the heat flux to the coating, which is what we are looking for, but also give some strain tolerance. It's a ceramic material, but if the substrate expands, having those splats, interface between splats are very useful and important to have good performance of the coatings. In terms of evolution of thermal spray over the last 50 years, a lot of people have worked, I would say, over the last 50 years to improve the process. We have seen the development and establishment of new technologies, starting from low pressure plasma spray to HVOF, cold spray, suspension plasma spray, and solution precursor plasma spray. We'll have presentations about that this week, and I will come back on suspension plasma spray later, and more recently, plasma spray PVD systems too. And in parallel, we have seen improvement in terms of control strategies and process control strategies. Beginning with mass flow controllers, and after that, computers, consoles, in-flight particle sensors, integrated process monitoring, in production, recording all process parameters, or most of them. And finally, we see more and more neural network and applications in that domain. Again, here we have, the big contributors to development of the technologies in Limoges, I have also, Fauché, Boulogne, Chevrolet, And all models also were developed during that time. And I would say Professor Vadel will speak about that later this week. So now we'll look at what's going on in the future. Clearly, we are facing a digital revolution, as you know. A lot of different digital and innovations, Industry 4.0 concepts, Internet of Things, digital twins, and now the development of and the number of application, growing number of application of machine learning, artificial intelligence, and deep learning. So we can expect that all those digital innovation will have a strong impact on thermal spray processing for coating and process optimization, but also for improving the process control in production of those coatings. In the example of plasma spray, you have here some sort of summary of the key parameters that needs to be controlled or that are involved in thermal spray. In terms of input parameters, current and gas flow rates, etc., powder feed rates, and surface preparation. The operating parameters, voltage fluctuation, the particle trajectory. I don't want to go into all details, and substrate temperature. We'll see that, important parameter, if we were able to control the particle condition of each individual particle, controlling the temperature, velocity, and trajectory, as well as controlling the substrate temperature, you can control the key parameters influencing the coating structure. But we don't have that control of each individual particles, as I've already mentioned. So it's important to look at the evolution of voltage fluctuation, and deposition efficiency to get a good understanding what is going on, to be able to optimize the coating properly, and also to ensure good, I would say, process control. There are a lot of, you have seen a lot of parameters here that influence the coating structure, but almost all those parameters are a potential source of variability in the produced coatings. When I started working in thermal spray a couple of years ago, the feedstock consistency was a big issue, but now that has been well understood that the particle size distribution is extremely important and has to be controlled, and still some variability, but much better control than before. And again, the inputs, everything here, you have some electron wears that we will discuss about that. Substrate is important also, and human factors that can intervene, but they are more and more, less and less important. In terms of, if we look at the time dependency of those source of variability, the electrode wear, we'll discuss later about that, occurs in the period of time about hours or 10 hours and 20 hours, in that range. Substrate temperature evolution from a few minutes to hours, depending on the size of the substrate. Powder feeders can introduce some pulsations also in feeding the particles. The power supply, 50 or 60 hertz, depending on the zone where you are in Europe or America or in Asia. But also the arc movement in the plasma torch. Again, we'll see that the arc fluctuates at frequency in the range of 2 to 5 kilohertz, and that introduces also some variability in the coating process. So particle diagnostics are used today to better understand how spray parameters influence the particle characteristics. And finally, also after that, how the particle characteristics influence the coating properties. Very useful to validate numerical models, and we'll see that models and diagnostic, they go hand by hand. And together, they can provide us a very important information to understand and control the process. Actually, it's used for optimized coating properties and monitor spray processes in production. To my knowledge, today, there is no closed-loop system extensively used in production, but the future may change that. We can see a significant change in the coming years with all the digital technologies that we have mentioned already. On the market, there are different commercial sensors. We spoke about already about the aqueous spray and DPV there, but also spray watch and PFI. All those sensors look at typically the thermal radiation emitted by the particles, and from that measuring the individual particles. In some cases, and for each particle, you can get temperature, velocity measurement with the DPV, for example. Others have some sort of ensemble measurement for the aqueous spray and spray watch, ensemble measurement for temperature, but individual particle for velocity. So you have different, I would say, detection scheme, and it's not the objective of to review that today. Now, after having seen that, I would say, background information, if we look at the current challenges that we're facing, I have already mentioned plasma fluctuations. Actually, as well demonstrated by Fenders, probably I have a citation here in 95, but before that, clearly he started with Eberlein to look at the dynamic of the arc and showing clearly that the electrons move from the cathode tips and you go with the arc route here on the anode surface, and that arc attachment point is moving on the electrode. If it was stagnant, the current is so high that you will melt and vaporize the material there. So the arc has to move. And that movement here, because the gas pushed the arc foot downstream, and so the distance between the attachment point and the cathode increase, so the voltage increase up to the point that a new arc can be initiated. So you can see fluctuations like that. And if you go the Fourier transform, you see that the frequency in the range of few kilohertz, in that case here, slightly below 5 kilohertz. The range of power variation can be very important, I would say, from 20% to 100%, depending on the fluctuation mode that occurs there. Again, Eberlein and others have studied that and speaking about takeover and restrike modes. In the restrike modes, we'll see up to 100% fluctuation. So that is the magnitude of the power fluctuation is the same size that the mean value actually. Those fluctuations have significant influence on the treatment of the particles, as you can imagine. These are images, high-speed images taken, studied in Limoges a few years back, 2004, close to 20 years ago. You see that the plasma here at different moments has different lengths, and the trajectory of the particles are significantly different when they are injected. And the speed, the power, the instantaneous power may vary by a factor 2 and more. So you get a significant fluctuation in the trajectories and heat and momentum transfer. We have been able to do that kind of time results diagnostics at one point, and we show that the fluctuation in the mean temperature of the particle fluctuate at the frequency of the plasma fluctuations, actually 4 kilohertz. And again, you have, so that is, you have particles that have heated at high temperature and others that much lower. You see here the difference over 400 degrees Celsius fluctuation in the mean temperature of the particle. So again, important. And we have seen that those fluctuations may influence significantly the coating structure. In this study here, 2 spray conditions were investigated, one with high hydrogen and low current, and in creating a big fluctuation, as you can see here. The other one with high current but low hydrogen content in the plasma gas, and the magnitude of the fluctuation much reduced. In both cases, the temperature, we adjusted the conditions so that the temperature of the particle were the same. The slight, in this case, here in conditions 2, the velocity was slightly increased as compared to this, but we were targeting here having significant, or as close as possible, similar mean temperature and velocity. And those 2 coatings here were produced in those conditions. And you can see that in the highly fluctuating conditions, you get porosity 7%, DE was reduced to 48%, and you can see the unmelted particles embedded in the coating structure up to 2,000 unmelted particles by square millimeters on the coating cross-section. In a more stable condition where the fluctuation was, the amplitude was significantly reduced, frequency was higher, the porosity, 4 to 5%, DE is significantly higher, and the number of unmelted particles was also close to 100 magnitude lower than in the fluctuating condition. Again, that shows that monitoring and controlling the mean particle temperature and velocity is fine. I would say we'll see example of that, but it's not the whole story. The fluctuation have to be taken into account. In suspension plasma spray, it's one of the new processes I mentioned in the previous slide, in one of the previous slides. Here, instead of injecting particles or powders in the range of 10 to 100 microns, we inject a suspension of submicron particles. So submicron particles are put in suspension in a liquid, water or ethanol typically, and the plasma jet atomizes that suspension jet, and after that vaporize the solvent, water or ethanol, forming aggregates. And after that, the aggregates are melted, and these small particles are actually deposited on the substrate. In that case here, the size of the particles, it's around 1 to 3 micron typically. So at least 1 order of magnitude smaller, and oftentimes more than that in the regular air plasma spray. And that make it possible to create unique coating structure, because here the particles being that fine, they are deflected with the gas because of the presence of the substrate. So they impinge on the substrate at shallow angles. And that make it possible with that technology to create columns like that, or wider or narrower columns, or fully dense coating, depending on the operation condition. And here, one of the additional difficulty, the size of the droplets that will impinge on the substrate are not determined by the size of the particles in the suspension. It depends on the atomization and heat and momentum transfer and formation of those aggregates, and after that, the molten particles. So that add a degree of complexity, an additional degree of complexity. Model here can be very useful to understand a little bit more what is going on. And actually in that model, work carried out by Dr. Dalir now, she has done simulation of the plasma jet, taking into account the fluctuation, and after that injecting the suspension on that. And you see here, note that the magnification on the Y side is expanded as compared to the X direction. And the size of the particles, this is represented visually as a 5 micron particles. We see that we have some suspension droplet that are not heated or close to room temperature, but those that penetrate well are heated at high temperature and melted, as we can see for the process. Again, here that was carried out with a fluctuating plasma. The beauty of a model, you can change the physics right away, having a plasma with or without fluctuations, voltage fluctuation as we've seen. This is the penetration of the suspension. The trajectory of the particles are located between those two lines, so well penetrated in the plasma when we have voltage fluctuation. Actually, the injection condition of the suspension were adjusted so that you have good penetration. But if suddenly you turn off the fluctuation, clearly you see that change totally the trajectories of the particles, and not only the trajectory, the temperature, velocity, and diameter. And we can understand that having that kind of behavior, especially for suspension plasma spray, you change totally the process. And so depending on the fluctuation conditions of the plasma, so something that is extremely important on the final coating structure. So you can adjust the injection conditions of the suspension, taking account of the fluctuation. But one key difficulty is the fluctuations are not stable with time. The pattern of fluctuations change with time. Actually, here you have an experiment where we started spraying with a new cathode and anode, and it's a picture taken from the front of the torch. We see the tip of the cathode here and the anode that is quite a smooth surface. And when you start using a torch like that, you see after a certain number of hours a degradation of the surface condition. In that case here, we run the torch and start and stop 2.4 times, mean value of 2.4 times per hour to simulate what is going on in production, for example. And with that, you can, we have discussed that the arc root is moving on the coating surface here. But with those peaks and valleys, clearly the arc does not behave the same way. And the consequence of that is, if you look at the mean power and you see a drift, if you keep the current constant, typically you see a drift in the voltage because the arc tend to attach closer to the cathode because of those peaks and valleys. You have tip effects and the arc root. It's a very difficult process to capture in model or the physics, but this is what occurs here. And what are the consequences of that? It's an example here. What at the beginning we had, highly low amplitude fluctuation. This is the Fourier transform of the fluctuation spectra after 0.4 hours of spraying up to 49 hours. And we see clearly that a main peak here start evolving. And so the frequency of fluctuation and the magnitude of fluctuation change with time. And you can understand how it can affect the coating structure, especially in the suspension plasma spray. So big challenge to keep in mind. In terms of process control, even if we have that, if we have heavier particles, they are heating in many cycles of the plasma because plasma fluctuation are in the range of a few kilohertz. So particles, a zirconia particle, for example, 40 micron, will experience a few cycles before reaching the substrate, a few high and low power cycles. But in that case here, what we have done, we sprayed the coating, zirconia coating after 3 hours. The electron was 3 hours in use. We got good coatings with cracks like that segmentation cracks that are positive attributes for thermal barrier coating to limit the residual stress in the coating, and got a deposition efficiency of 55%. After 37 hours with continuous start and stop, keeping the current constant, in that case, now the power dropped only by 1.5 kilowatt. It's not that big, but the coating structure changed. No more cracks, and the DE was reduced to 41%. At one point, we changed the spray parameters to come back to the same or very similar mean particle temperature and velocity. And we got a coating like that. So cracks are back and deposition efficiency almost the same. So that shows that controlling the mean value of the particle conditions, speed, and it's bringing us in the right direction. But as we have seen previously, it's not the whole story. So we need to have eventually other elements, taking into account eventually the whole distribution in the temperature velocity of the particles. One danger that we see in production in many places to compensate for the drift in voltage that we have seen there that is natural, operators are permitted to increase the hydrogen flow rate to come back to keep the power about at the same level that you get at the beginning. But one danger associated with that, more hydrogen means higher fluctuation. The magnitude of the fluctuations tend to increase. So maybe it's not the right way to proceed. We have seen that increasing the current provide a good compensation globally for the drift in temperature and velocity. And with that knob, it's probably and that has less influence of the magnitude of the fluctuation. So some challenges associated with the torch and the heat and momentum transfer to the particles. Now, if we look at what's going on the substrate when the one droplet impinge and flatten and solidify. It has been observed for decades of many years that you get different splats. Again, one droplet solidify, we call it splat. Sometimes you have figures like that, some other times very nice disk. But it was clearly shown by Dr. Fukumoto in the mid-90s that the key driver for that was the substrate temperature. So you get something like that at room temperature, and 400 degrees Celsius, you can form almost perfect disc. And that transition from that pattern to that one occurs for almost all, not exactly, but you see here, I will come back here first, the splat shapes, comes from, you have about 20% here of splat at room temperature. And when you increase at one point, if you go to above 600 degrees Kelvin or 300 degrees C, now you get 80% of a nice disc-shaped splat. So you have a transition occurring between 300 and 400 degrees Celsius, and for almost all materials in that range, the transition temperature. And in that case, yes, coupled on the same image, you see that the adhesion of the coating is much higher when we get a good number of those disc shape as compared to splat shape. So you can understand that this has a direct influence on the coating structure and properties. After that work, we were able to take picture, high-speed picture, a few nanosecond pictures of, again, molybdenum particles here on glass substrate, where we sprayed on glass substrate, on hot substrate. In that case, within 1 to 2 microseconds, the disc is fully formed, and after that, material solidifies. Sometimes you have a little bit of splashing, but most of the time you have a nice disc shape, as we have seen from Dr. Fukumoto work. But when we go on cold substrate, again, same particles, same spray condition, exactly the same. The physics that occurred there changed totally. In that case here, you can see that the disc size increase about by a factor 2. And you can rapidly have very large discs. And after that, the disc, these are picture taken at different moments. Initially, you form a large disc. After that, the disc start breaking around the center portion and somewhere randomly in different location. The number of holes like that increase with time, and because surface tension, they retract, leaving at long term that kind of images. And you see here an image very similar to the one shown by Fukumoto. Again, that shows that experimentally the disc is fully formed, and after that it breaks. And so what's the reason for that, and what are the consequences? In terms of consequences, I would say very nice work by Dr. Kuroda in 1995, mid-90s, looking at the influence of the substrate temperature during spraying on the porosity as measured by a mercury infiltration. If you spray at 440, so it's about 150 degrees Celsius, you get a lot of pores in the range of 100 nanometers, between 10 to 100, or most of them here around 100 nanometers and a little bit less. And that corresponds to the gap between the splats, as we have already discussed. But when you increase the temperature during spraying, you see that amount of gaps decrease. And I think that shows similarly here. Here we have been able to show that the liquid disc actually does not touch the surface. It flies over the surface. It's why the liquid can break the way it breaks here. So we see same thing in the body of the coating too. And another example here, we measure zirconia coatings here, sprayed exactly same condition, but substrate temperature 200 degrees Celsius, and here slightly above 400. And we measure the elastic modulus by measuring the ultrasound, the velocity of the ultrasound in the coatings to measure the speed parallel to the substrate. And we saw an increase in the elastic modulus by 50%. Again, everything is the same except the substrate temperature. And it's really linked to the quality of contact between the splats. So that has influence on the elastic modulus, residual stress, permeation, strain tolerance, etc. These gaps here and that different behavior of single droplet impact of smooth surface or the gaps here, though the reason for that has been associated with adsorbates. When you have a surface at room temperature, humidity or maybe CO2 can adsorb at the surface, and that material can desorb upon contact with the molten ceramic or metal particles, because again, they can desorb at room temperature. They are stable on the surface, but can be detached and desorb rapidly when heated by the particles. Actually, we were able recently to test that hypothesis, and I go rapidly here. We assume that there is some adsorbate on the substrate. It's modeling work, and we get desorption here at the edge of the liquid. So you have the zone of gas desorption that expands with the, or that moves with the tip of the spreading particles. And doing that, again, the results of modeling here rapidly, you have a droplet. The beauty of model, you can have with and without gas desorption, everything the same, the rest being the same. If you don't have gas desorption, you get a good flattening. Again, the initial condition after a few times period, you get a nice flat. Here's an image of that zone, but magnified in the Y direction. And we see a nice disk that was formed. It's axisymmetric, and the black zone here is already solidified, and the rest is still liquid. But you get a good, something that as you can expect. But as soon as you start putting the desorption, you see the detachment of the liquid here, and so after that, the liquid flies over the substrate, making it possible to expand on much larger surface. And after that, it starts to break. In the modeling result, we have more breakup here, and it's likely due to the finite size of the cells that are there. Because as I mentioned previously, the liquid thickness here is less than 1 micron, in the range of between half micron and 1 micron. So in terms of cell size, it's getting complicated to that creates some instabilities, breaking the film. Having said that, I hope I convince you that substrate temperature is a key parameter to control. And again, that has the substrate temperature into the first of all those parameters. The beauty, it's not too complicated to measure during, in production. You can have optical pyrometers or infrared cameras that can capture variations, and it's the right tool to go forward with that. Now, looking at, that was some of challenges, I would say important challenges that we still are facing in terms of gaps to address. First, in terms of particle sensors, I would say we have seen that the main drifts that are cause problem, we cannot do anything about the fluctuation at high speed. We can develop new equipment. As you know, there are some torch with cascaded geometries that make it possible to get longer arcs, more stable one. And Professor Valdel will speak about that later this week. I'm sure about that. But so in the typical plasma torches, the erosion of the electron, the electrode wear occurs in the time period of hours or 10 hours. So the current sensors are precise enough. They are able to detect particle fluctuation, or in terms of mean value of a few 10 of degrees Celsius, and they can provide that kind of measurement within seconds. So I would say for typical plasma spray conditions, it's fine. But as we have seen, there is emergent new processes that see more and more industrial application, SPS and suspension plasma spray and solution precursor plasma spray. In that case, here it's much more complicated. The size of the particles are typically around 2-3 microns. So the individual particle measurement are not able to do that, to measure, for the thermal radiation. And the size measurement becomes, now we don't know the size of those droplets because they result from the atomization of the suspension, the atomization conditions and solvent evaporation. So quite a significant challenge here in terms of size measurement. So far, up to 5 micron, it's not too bad, but below 1 micron or around 1 micron, it's still very difficult. And because of the small size of the particles, because of the presence of the solvent, you may have radiation emitted by the plasma, by the vapors that can perturb the temperature measurement also. So in many cases, The speed measurement of the particle is not too difficult, but the temperature in many cases, it's not possible, especially that the spray distances are relatively short in SPS. Similar, I would say, challenges for cold spray and warm spray. Now you spray particles that are close to room temperature, maybe 100 degrees Celsius, maybe a little bit higher than that, but not much in many processes. So the sensor based on silicon detectors that are, all the current sensors are based on that, they cannot see anything. You know, if you look at cold spray system, you look at the particle jet, you don't see anything because there is almost no radiation emitted in the visible range or near infrared. You have to go in mid-infrared around 10 microns. And actually some progress have been done on that recently. Alexandra Nastic and Bertrand Jaudoin from Toronto, published that paper 3 or 4 years ago now, looking at a high-speed high-speed infrared camera with sensitivity around 10 micron, and they were able to detect the particles. They cheated a little. They put here larger particles to be able to make sure that they can get reliable temperature measurement. Very useful to, I would say, to validate the results of the modeling work, but still not in the typical cold spray condition where the particle size are mostly around 20 micron. But more recently at Jülich, we've seen that they have done similar work with a different camera, but we are getting closer to good measurement of temperature in cold spray situation. I think we have seen that we cannot control the condition of all particles individually, and controlling exactly what occurs on the substrate, humidity and gas absorbed there. So having ways to measure in situ the coating properties during deposition or just before and after might be very useful. And again, with the new algorithms for process control, all that information can be taken into account. It's an example here of the ICP-8. It's a technology commercialized by Brillia Coat Technologies. It's based on technology developed at Stony Brook by Dr. Sampath, who will speak after me today. It's a nice technology, making it possible to assess the residual stress and elastic modulus of the coatings, but during spraying. But what we're looking for also to add on that is clearly to have online measurement of other coating properties, ideally without contact. So thickness, roughness, density, thermal conductivity, etc. Again, if we can get that kind of information to provide to the machine learning algorithms, I think we can improve the quality of the control. Coming back here to, after discussing that, clearly voltage fluctuation, good understanding of the control and monitoring of particle temperature, velocity, and flux, but not only the mean value, but eventually the whole distribution and substrate temperature are amongst the parameters, those that needs to be, transfer forming, you can, with all the characteristics of these parameters, controlling and monitoring everything in terms of input parameters and maybe other operating parameters, as well as substrate condition, will feed a lot of good information for process control, as we'll see later. Numerical models, again, they work hand by hand with sensors. They investigate the influence of specific parameters that we cannot do in reality, putting on and off the voltage fluctuation or the presence of adsorbate at room temperature. Virtually or in the models, you can do that and see the influence of some parameters. Experimentally, that might be very difficult. Complement data from sensor. Sensor provides some data, but in the background, you can generate more data from some validated sensor measurement, but also you can understand what is going on in the process. And again, with the data from sensors, the models can certainly feed data for learning algorithms for in machine learning. And I would say, when I say modeling A to Z, it's modeling the torch operation to the coating buildup and eventually up to the prediction of the coating properties for the targeted application. In that case here, just an example where we start modeling the process itself, the injection of the suspension, put a substrate, look at the deviation of the particles. And so in that case here, we can determine the condition of the particle just in front of the substrate. And based on that, you have the spray, the substrate, taking the particle condition just at 100 micron above the surface and find where they land on the substrate. This is the pattern in that experiment here. You have the trajectory of the particles between a planned 100 micron before the substrate up to the substrate surface. And so here, and we use that one particle at a time taken randomly to add on the surface of the coating to simulate the growth of SPS coating. This is the type of work carried out by Behrad Kashfi a few years back. I would say his thesis is at Concordia, and shows examples of results. Again, one particle at a time, those coating will build up, moving the torch virtually in front of the substrate and trying to replicate, and that make it possible to study the influence of the roughness or the speed or the size of the particles, complementing very well the what we can get in terms of information from the models. To finish now, I would say rapidly, I'm a little bit late, machine learning and artificial intelligence that make it possible to collect and analyze a large quantity of data beyond what our brains are able to do. At one point, if you have 3 or 4 dimensions, after that, we're lost. But with those algorithms that make it possible to cope with that large quantity of data and make some sense of it. These technology, I think, will transform the way research is carried out in thermal spray. And I'll show you an example where we can adjust the coating condition. You don't have to do all experiment, but you can predict some coating characteristic and structure. And as we have seen, a number of studies have been already done over, I would say, the last 20-ish or 15 to 20 years. But now to apply the neural network and machine learning algorithms through thermal spray, but the number of, I would say, work on that domain, number of publications is rising rapidly at this point, because there is a very nice opportunity here to really transform the way we do thermal spray. So algorithms of machine learning algorithm are trained by data collected by the sensors. All parameters, we have discussed about that, and images, you can imagine, you can look at the surface of the coating, cross-section, coating characteristics, measure online or offline, elastic modulus, microstructure, surface profile or cross-section, etc., plus the results of computer results. And you have now tools like black box optimization that make it possible to ingest all that data from different sources and making some sense of it. That may give us a very good way to have robust closed loop control system. I would say today, almost I've seen a few examples of application of closed loop based on particle temperature, but it's quite rare and limited. It's not well, I would say, used in the industry. But a well-trained machine learning and artificial intelligence algorithms have really the potential to produce that kind of robust modeling or results. Recent paper published in JTST last year actually shows an example of that, where 2 artificial neural networks were used. The first one from the having as an input layer the spray conditions, spray parameters on the torch. Here it's for HVOF, and with the neural network predicting the particle temperature and velocity at the location of the substrate, and a second network that take as an input parameter the temperature and velocity of the particles, and compare with the porosity, the attributes of the coating. So coating properties and eventually even performance, I would say, assessment. So you have a way to predict the particle temperature, and after that, from the particle temperature, predict the coating structure and properties. A rapid example about that is carried out at University of Toronto by Part Mahendru and Musa and Dr. Dolatabadi, using some former research we have carried out on suspension superhydrophobic coatings, where they took the data from a previous publication looking at different spray parameters that have influence on the coating structure and superhydrophobic phobicity, use that as an input to teach the machine and deep learning models, and making it possible to get prediction after that. Again, the data was taken from published data a few years back, and looking at, in terms of output here for the wetting characteristic, the sliding angle, so the angle at which the drops start moving on the surface, and the contact angle, and also from the output image generated by a generative adversarial network. Again, I'm not specialist in that, but it's a good way to establish, to build images to be able to compare. You know, with the data that was provided from the paper, the already published paper, the intent of data pre-processing, the software identified rapidly that the column density had a very strong influence on the sliding angle. I would say in that case here, that was relatively simple. Our brains were able to extract that information. But in that case here, that was done automatically by the system. So which is good, because again, the artificial intelligence approach has the potential to do much more complex analysis than what our brain is able to do. And so in terms of example of results here, we can set up now a series of input parameters. With that, the system is able to predict the contact angle and the sliding angle. And the GAN model prediction also can, I will try to start that. Oops, okay. I don't know why it does, okay, now it moves. So it's different iteration of the process. And we saw, okay, sorry, it does not work. Okay, now it's converged. And at what point, if everything goes well, it will stop, where it's the final image that would, you know, it's, if you spray a coating in those conditions, you expect having a coating with that surface structure and getting that contact angle measurement, and I would say contact angle and sliding angle. So that shows the strength or the direction in which we are going. So we have to carry out some experiment, but feeding the algorithms with the right data is a very powerful tool. So in terms of conclusion, I want to say that thermal spray processes are extremely complex, making them difficult to optimize in coatings. Over the last 50 years, important progresses have been made by different generations of researchers and in the university labs, in the national labs, and in industry that provided better equipment. I've not talked much about that. I know that Dr. Valdel will speak about that kind of cascaded torch later, but better sensors and better models so that make it possible globally to improve the process consistency and quality of coatings. But now I think with the arrival of machine learning and artificial intelligence, that will really drive a quantum leap in the quality of spray coatings and closed-loop controls. For those interested, I would say with Georg Mauer in Germany at Jülich, Germany, and myself, we published recently a perspective paper on those topics here that was published a few weeks ago. And something in terms of, when we think in terms of digital twins and Metaverse, a very, very interesting presentation, and I encourage you to have a look on it, given last week actually by Bertrand Jaudoin on thermal spray and Metaverse. And he shows what are the possibilities and how the future looks interesting for researchers in the coming years. So thank you very much. Sorry, I've been a little bit long, but not too much, a little bit longer than expected. Thank you.
Thank you so very much, Christian. That was splendid, and time-wise, it's quite okay, no problem. So there are a couple of questions I will probably moderate and say it here. So the first question has come from Vish, who is working with me at LSPU actually, and an ex-GE staff. And his simple question is that, as we know that cold spray is a high velocity process, can that be monitored using high-speed camera?
Which one, sorry?
Cold
What
spray.
process? Cold spray, yes. The speed, I would say in general, the speed, it's not an issue. You can have a laser eliminating the particles and you detect the scattered radiation with high-speed sensors, optical sensors, very easy to measure. It's not for all spray processes, independently of the temperature speed, it's one of the easiest parameters to measure. So no problem to go with the, you had some time to modify the previous generation of sensors because they were not designed to work at 1,000 meters per second. But now, it's easy to move that way. It's not an issue, not in my mind at least.
Two more questions, Christian. One is from Jiao Sun, and the question is, I was wondering, can machine learning be used to optimize the coating microstructure?
Absolutely. I think, and the last example I gave, I would say it's for me, it's a good example of what is possible in that. You carried out a certain number of experiments, get the coating structure and some of the properties, feed the data with in the machine learning algorithms. And after that, you can create virtual experiments from that data. You can validate in some cases, but that will guide you right away what knob to play to get different coating structures and eventually also different coating properties. And I think for coating optimization, that will create a very nice way. I remember a few years back, we had the Takushi approach for coating optimization or process optimization that limited the amount of data that you can do, and that takes a good number of experiments. But I would say with the more robust algorithms that are now available, I think for coating optimization, that would be a very strong tool in the coming years. And we start seeing good examples of that.
Okay. One question from Eric Cox is there any requirement or potential advantage in being able to chemically sense or monitor within the PS environment? Oh, sorry, thermal spray environment.
Can you repeat, please?
Is there any requirement or potential advantage in being able to chemically sense or monitor within the thermal spray environment?
I'm not sure I understand the question correctly. If in some cases today in production, sensors are mandatory, not for thermal barrier coating systems. That technology has been developed 30, 40 years ago. So sensors were not available at that time. But if you look at the coatings on the landing gears in the aerospace, it's a critical component, as you know. And the replacement of hot chromium occurred about 20 years ago, and sensors were available. And now for different landing gear manufacturers, having a sensor during production to look at the particle conditions and particle jet conditions, it's mandatory. It's part of all the data coming with each part, at its own personal, I would say, identity. All the steps in the manufacturing process are taken, monitored, and registered, and particle conditions during spraying are among that.
Sure. Maybe I can see, Christian, one last thing is my colleague Gustavo is holding his
Hi,
hand.
Salvador.
Hi, Christian.
Thank you for the nice presentation. I have a follow-up question on the machine learning. So one of the pros of machine learning,
I must admit here, a disclaimer, I'm not an expert in that domain. Okay.
That's fine, but you're certainly an expert on the experimental part. So my question is, how do you see the difficulty of gathering enough experimental data to feed machine learning?
It's a very good question. Getting enough, but during spraying, if you imagine that you are taking data, you are in production, you install a system, and you use the actual production, you take the same usual way to validate your process, and you learn during, you make your algorithm learning for the specific coatings you want to produce. And I think after some time, you can get very confident that what the system will provide you is very pertinent, I would say, in terms of parameters to be controlled and the way to control it. But we have to make sure that the right information is there too. For example, if you don't monitor the substrate temperature, and we see you get variation in that, as we've seen. If you don't monitor the plasma fluctuations, I don't think, you can take noise also, in the past for maybe for those of you who started doing thermal spray with the operator being in the spray booth and doing all that, the operator knew right away if the torch was running correctly, because the noise was a good sign of the operation condition of the torch. So good sensors that provide good information, valid information though. One difficulty, I had some discussion with people, taking, for example, if you go back and try to look at the cross-section you produce over the last 20 years and to feed your, as you may know, if the polishing procedure is not perfectly well controlled and consistent, the same coating can look very differently from depending of the way the coating have been cut and polished. I remember we get study was carried out, the same coatings produced at the same place at the same time was shipped at 3 or 4 different locations. And the assessment of the coating porosity changed by almost a factor 10, depending on what it was. So that was amazing, the variability. And again, here, if you don't have right data to feed your algorithm, you cannot expect a miracle here. So I would say, in my understanding, it's important to make sure that the quality of the data is good and as extensive as possible, and let the algorithm to define what our brain is no more able to do, playing with all those parameters. Again, having, for example, the particle distribution and not only the mean value and maybe even the mean value standard deviation, but the whole distribution of particle size, particle temperature, velocity. Our brain is not able to cope with that. There are too many parameters. That doesn't mean that those parameters are not important. It's just limitation of our brain. And I think with the algorithms here, that limitation does not exist anymore.
Perfect. Thank you very much. Very interesting.
Thank you, Christian. So I think, Christian, everybody would like to thank you for this splendid presentation. And we can see in the chat box, a lot of our audience are very grateful and thankful to you for this splendid talk. And if there will be any more questions, we will direct them to you through email. But in the interest of time, we can now move to our next speaker.
I will be pleased to answer the question offline eventually.
Sure, we will do that.
Thank you very much again for the opportunity to discuss with you today.
Thank you. So we now move on to our next speaker, Professor Sanjay Sampath, who can now be seen online. So I'd like to begin, first of all, by saying, maybe with your permission, Sanjay, that I would hold you as one of the finest exports of India in the thermal spray coating sector. He's currently distinguished. Now you two can actually debate on that. To be you both are champions in this area. Is currently a distinguished professor of material science at Stony Brook University, SUNY, and director of Center of Thermal Spray Research, which is an interdisciplinary industry-university partnership in the field of thermal spraying processing. And it was created in 1996 through the National Science Foundation, the NSF funding body in the US. Professor Sampath received his bachelor's degree from the so-called now Indian Institute of Technology in Banaras Hindu University, and his PhD from Stony Brook in 1989. And after graduating, he spent 4 years in GTE, Sylvania, involved in research, development, and processing of refractory metals and compounds and composites. By joining Stony Brook in 1993, he directed research on various federal and industrial funded programs. Particularly under the auspices of the NSF Center, he directed a group of a dozen or so interdisciplinary faculty members towards fundamental understanding of the spray processing materials and application. And then the self-sustaining center since 2005 came into being, which is home to the Industrial Consortium for Thermal Spray Technology, which is comprising of 35 leading companies in the area, which was aimed at knowledge transfer from fundamental research to the applications. He was also a principal investigator on the DARPA Mesoscale Integrated Conformal Electronics project, enabling 3D printing of sensors via direct writing of thermal spray technology. He holds about 220 number of papers and maybe probably more by now, 15 patents and a number of awards that he has been. Recently, he has been inducted into ASM Thermal Spray Hall of Fame, received Application to Practice Award from TMS, and in 2019, he received the John Jepson Award from American Ceramic Society, and in 2020, ASM Albert Sever Award, and so on. List is short, but his accolades are far more. So with that brief introduction, Professor Sampath, I'd like to invite you to give us the second talk of the day.
Thank you. I hope everybody can see my screen.
Yeah.
Okay. If anybody doesn't see it, move forward. Sometimes it happens on my machine, and please let me know. First of all, thank you all for, thank you, Sarah, Pamela, Alan, for inviting us. Obviously, Corona has had changed some things in a very positive way by really actually bringing the world together, both by infecting all of us, but also allowing us to talk much more uniquely through these forums. So Christian talked about the future. I'm going to talk a little bit about the past. And when Sarah asked me to talk about the technology evolution, this has been sort of on my mind for a long time. We've been talking about history because past is prologue, as you know. So I'm going to share with you sort of what I have gathered over the years with help from my colleague, Professor Herman, and other industrial practitioners in this field in the US. So most of my talk is US centric, but I hope you will appreciate how this technology has come to being, especially a lot of the young people who are attending these this forum. The second part of my talk is to pivot and talk about sort of, how we will think, how we can move forward in this concept, what we mean by the word innovation. It gets thrown around a lot, and I urge people to actually read up about it and understand it a little bit. So obviously this work is not possible by me alone. There's a lot of people who have contributed to it over the years, and the list is so big that I obviously cannot include all of them in this slide. So I'm going to basically cover many years of information. So let's talk a little bit about the big news, right? The advantage. Thermal spray coatings have wide-ranging applicability. You've got, of course, the aero and the space domain. You've got the heavy machinery. You've got textile. You've got infrastructure. You've got oil and gas, implants, automotive, and electronics. Very rarely is there a process that encompasses all of these sectors simultaneously. And so we typically refer to this as a platform technology, which means that it is a core competency that can be applied over a large number of industrial sectors. And so which means that there's a need for it. And there is obviously a lot of success associated. But I can also point out to you a lot of the challenges in implementing thermal spray. Christian already covered the complexity of the process. So we've remained in sort of this black box or gray box scenario for a very, very long time. It is very difficult to increase the sophistication of these things. So we end up becoming knowledge-centric, especially experience-centric. So why do we use them? As I already mentioned, that it is a platform technology, which means that it addresses critical issues in lots of different industrial sectors specific to those engineering components. Second, it's flexible, scalable, reconfigurable. What does that mean? you can take the same spray booth and you can do multiple materials. You can add spray booths and you can do more coatings. You can add more processes within the spray booth. It can potentially be reconfigurable if somebody wants to go from plasma spray to HVF or HVF to suspension spray. Most of the physical infrastructure, to a large part, can be relatively easily accommodated. That's not so true for thin film, certain thin film technology and certain plating technologies. So that's very unique for thermal spray. And that's why we believe that it's been around for 100 years and will remain for another 100 years. And thirdly, it is becoming, I would say, a core competency for lots of areas. And this is where there is I see sort of some red flags ahead, because thermal spray is not part of the traditional engineering education curriculum. And how do we make sure that this knowledge is appropriately captured? So how do we think about them? So you can treat them in sort of 4 domains categorically. One I call duality of function, where you've got a substrate that's supposed to provide strength and the coating that's supposed to, let's say, provide environmental resistance. The second application is when you want to add a high value material on a relatively low substrate. You want to do stainless steel on steel, or you want to do lanthanum manganate on a chromium plate, or you want to do titanium on a cobalt moly alloys, things of that kind, where the bond coats, advanced bond coats, for example. Third is enhancing performance. TBCs or any of these other systems, of course, add biomedical implants. They provide better performance aspects. And then the last, of course, is can I reuse it for reclamation, which is the sort of also a very important aspect of how to sustain an engineering material. So these are the sort of the 4 characteristic domains of the systems. So then we can go back in history and study how did we get here, what were the key milestones. So if you look in the early years, and those were some really interesting grainy pictures, and I'll go through the few of them as we go along. Sort of the first idea of using thermal spray actually started with material restoration. Mostly using flame spray, wires, and in some cases powder. I don't think even arc spray existed in those days. Mostly it was flame spray. And so the idea there was that can we take extremely large metallic surfaces and try to reuse them because of simply cost and manufacturability and so on and so forth. This idea has now come, roaring back with the idea of metal sustainability and the circular economy, where you would really want to not throw away a piece of steel or aluminum or titanium that has gone through enormous amount of energy consumption to get it from its ore to an end product. So coatings provide a great platform, and that is now called remanufacturing, which was largely introduced in about 30 years ago through the framework of what's called remanufacturing, while the aerospace industry has always used coatings as a platform to allow their components to sustain longer operability. Following that, the big area of impact was corrosion. You can see some of these large area, metal tanks that were protected with catalytic protection using aluminum or zinc. Then around the 60s, things like the paper industry, the automotive industry started, but the real breakthrough came when the aerospace industry started to implement these coatings in fairly systematic manner in the aircraft engines. The automotive industry, which was doing high volume in the 50s and maybe in the early 60s, also came back, and I'll spend more time on this. And then along the way, lots of other industries have come along. Obviously, landing gear, Christian talked about. The semiconductor is a big user. And there has been uses of functional oxides like LSM in the industry. So this is, you can see that it's, again, a broad domain. I'm sure I missed out quite a bit of these things. This is just an illustrative example of the applications and the milestones. So we can go back and ask the question, sort of, what gave this kind of pivot? And I'll go through this technology S-curves as we go along. So what contributed to these successes? And maybe that'll be sort of the end game that I want to talk a little bit about. And sort of the main message is that what drove it were the system design needs. And I'll give 2 examples, the aero engine and the cylinder bore. to drive home this point that bottom-up innovations are very difficult, but top-down is usually more adapted, but the top-down takes much longer to go through the validation process. So, we are sitting here in 2023, and I have in my office, thanks to Professor Herman, a series of books that literally goes back to 1940. I'm sorry, I took these images on my iPhone, and I'm not good at this, but this is August 1940, Metco News. This is 47, 52. Mogul was another important company in the US. And again, as I said, I'm only sharing American data because that's what I have. This flame spray handbook, and I'm going to show you some nice examples from here, is from 1963. The book by Ballard is in the 60s, Goodwin Hecht in the 70s. So there's been a lot of work that has been done. And if you go back in literature, you will really appreciate how our predecessors had thought through a lot of these things, even the stuff that Christian talked about was already in many of these handbooks and manuals. And so, obviously these get forgotten. These kinds of books are not available in Google Scholar, so we never look at these things. But there is an important message here that tells you sort of how we evolved as a community or as a technology. So just in the US, in the early years, following the Swiss invention, there was work done in the US, which led to the creation of a company called Metco. Concurrently, what's now called Praxair, it used to be called Union Carbide. They invented the D-gun that came by watching how, when you light street lamps, you get these micro explosions that created deposits, and they took that and they converted that into a technology which is still widely used today. Most of us don't ever use them because it is kept proprietary to them. And then, of course, the aerospace came in and made it part of their design parameters. That led to lots of people becoming familiar with it. There was a rapid growth. Then the aerospace deregulation came along and created business consolidation, which created some setbacks around this time in the early 1990s. And then it kind of things caught back up afterwards. Initial applications, I'm not going to go into the details, dental light bulbs, refrigerator cold plates, wood caskets. You can see how many things were contemplated with this idea of using these coatings. Again, not the greatest pictures. I got to figure out how to take these pictures better, but you can see lots and lots of applications in very large surface areas over the years in the area of corrosion. A lot of this doesn't happen. Paints have become very, very good, and so it's not so easy to replace paint with metallization. Again, this is something, a lot of the shafts and items, basically thermal spray became part of machine shops, where when something was like a divot or something was there, they would go in and patch it with flame spray. They'll get the dimensions right and then remill it. We talk about cold spray today. This is literally 100 years ago. This was done a long time ago. A lot of applications involving spray and fuse, where the coatings were not fully dense, so they would use these self-fluxing alloys and then basically reheat the surface to allow the fusing of these materials, so you get an extremely high quality surface engineered material for wear and corrosion. Molds, again, people have talked about doing molds. You can see how one could be used for replicating molds. Again, some of these pictures go back literally 70 or 80 years. Automotive industry was a big champion of this. Look at this example, 4,000 valves per hour was coated in the 1950s or early 60s. Molybdenum was a mainstay in lots of different applications, especially because you could use molybdenum in the form of wire and flame sprayed. Some of these things are still being used. And even in those days, people use sealants to protect the porosity from being used. You provide a pathway for environmental media to get in. I'm going to talk a little bit about cylinder bores, but this is circa 1960s, when here a flame spray gun with an angled exit is actually being used to deposit coatings inside a two-cylinder aluminum engine. Now, of course, in this example, the block rotates, not the torch, and that's the sort of the big change that happened later. Again, not belaboring the point, but if you look at some of these things, it's kind of very, very humbling as to what our predecessors did. If you look at many of the torches that we currently use today, from the MB torches, the Norton Rockite, the SG guns like the SG1, SG100, even the plasma technique F4 goes back 40 years. And because when I started my PhD, I was working on this. The PlasJet goes back also about 40 years. EPI vacuum plasma goes back to the 1970s. And of course, I mentioned that the D-gun came in the 1940s and 50s. So you can see that a lot of the ideas that we use today goes back at least 2 generations before us. Paper industry was a big champion, the Yankee drill. This is where people actually took the spray torches to the paper mill to apply the coating. And this picture is from the 1960, January 14th to 30th. A lot of space components, perhaps related to the the defense industry coming on board, where the ID spray, this is again the Rockite gun. And then the missile programs, the aircraft engines, you can see thermal barriers starting to show up as early in the 1950s. This is actually a 3MB gun spraying some of these coatings that long ago. And I don't know if you're familiar with the Rockite process. Basically, it uses a rod of a ceramic, and that gets to develop the ceramic coating in those sticks. Again, automotive industry, these piston rings and synchronizers go back again about 70 to 80 years. So a lot of the materials that we currently use today also came from that era. And when you look at all of these systems that are over there, there's many wires. The self-fluxing tungsten carbide, the molybdenum self-fluxing, they all go back to that era. And even the tungsten carbide, the chrome carbide, and what's now we use TBCs, they call it lime stabilized zirconia. Basically, it's calcium. Today, I can find them in the shelf, go back 60, 70 years. Now, this book in 1963, the thermal spray materials, I have it with me. And if you look through this carefully, it's rather busy and it's difficult to read. I would say a majority of today's materials were in this book. And look, they've even given you the recommended parameters as to how to spray these materials by plasma spray. So, it's, and you can see molite here, tungsten carbide self-fluxing band. There is obviously yttrium zirconate. They called it yttrium zirconate in those days, magnesium zirconate, lime stabilized zirconia, and fine tungsten carbide agglomerates. So that you can see that, a lot of the materials that we deal with today were contemplated and applied in production in those days. So the big sort of milestone, and I learned this talking to people, some of who are not even with us anymore, is that in the early 60s, there was a big interest to create a big bypass fan from Pratt & Whitney, and they had a problem with these mid-span dampeners, and they needed a coating, and that's when essentially tungsten carbide cobalt was born, and that led to sort of the first major insertion into a commercial aircraft. And both Metco, Plasmadyne, and all GE followed Pratt, and this led to this amazing growth, at least in the United States in those days. And that led to the spill-off into the land-based turbines, which lasted another 20 years or so. Significant involvement, a lot of these things from the US government and programs both from DoD and DOE that led to the acceleration. So right now, when we talk about how great all this, we are living off this sort of amazing legacy where lots and lots of different components, not just TBCs, from molybdenum to triboloid to tungsten carbide to aluminum bronze to cobalt, nickel, indium, all these materials get applied, not just for OEM, but because biggest market for all of these things is actually in the remanufacturing area. Again, vast majority of these materials are from the yesteryears. So what happened in the early 90s was the boom years kind of suddenly got affected because of deregulation that President Reagan initiated here, that led to essentially these high-cost air travel becoming much more common man air travel. That means the aero industry obviously had to really learn how to cope with better performance, lower cost, higher yield. Even the airlines started to do maintenance themselves to do that. And that's why you saw this little drop here, because the rest of the world had not picked up as much as Europe and America in those days, maybe with the exception of Japan. But in the mid 80s and 90s, other technologies came, notably in Japan with the steel industry, that allowed things to come back, and then the rest of the industry came back. These numbers have obviously progressed quite a bit. We don't have very good numbers in the past. But this is also the time where a lot of business consolidation took place between things like Sulzer Metco or Praxair, which was formed from combining Miller, Taffa, and the original PST. So many such consolidations in the thermal spray industry. And whenever there is consolidation, of course, it has the effect on innovation being not progressing at the same speed that it does. And that led to some slow growth for a while, but then things have picked up again, particularly with international, especially Asia, China, coming online and really pulling the technology forward. So let me just conclude sort of this part of the talk. I hope you got an appreciation for the fact that we're not doing a lot of new things. We have to appreciate that there was a lot of people who didn't have machine learning or sensors, who successfully implemented a lot of these coatings that we still currently use in our day-to-day life, whether it's using tissue paper or flying in an aircraft or going to space. A lot of these things were thought of and progressed, implemented, certified, and successfully used for decades before some of us were even born. Why did all this happen, and what was sort of the driver? So, and I'll talk about that from the context of, especially those of you who are starting off your career and where you're thinking about taking some of these ideas. And it's important to be cognizant of this knowledge. And some of us have gone through this process thinking that our ideas are fantastic and great, only to find out that somebody had already thought about it before, or somebody had thought about it, failed, and was not perfectly documented to allow it to reappear. So the important thing is the sort of two parallel efforts that took place. You had the companies at the bottom up, like Metco and Union Carbide in the US, that were actually pitching these ideas of solution, but you really needed the end user to drive home the rapid growth. And that required something like the aerospace applications, and then eventually the TBC applications and the advanced turbine systems. So what that means was, if you were really responding to these pull coming from the large OEMs, then your attention is directed at them. Some of the other sectors were sort of not really pursued with the same kind of vigor and enthusiasm that it did. And so if the system cannot decide what exactly it's going to need, then it's very difficult for the innovators to provide the solutions. So this connection between system, materials, and processes was kind of very limited across the board. And each sector had to kind of learn it its own way. And so in many of the applications, especially this pre-deregulation, where the aerospace was able to afford things, but in a lot of the other sectors, cost was still a very important virtue. And so as an industry, we were unprepared, and so we didn't have the luck. And last thing is that, people got by solving problems more like, I use the analogy of a fine chef who can figure things out on the fly, but that requires a lot of experience, wisdom, and knowledge that comes from actually doing the work, which is, as Christian mentioned, the operators. And then the third important thing is, any of these developments that you're thinking about took an extremely long time to become practice. And I'll go through this in a little bit more in the details, and why is that, and what took you so long. So let's just I'm going to focus on two examples. One, obviously, many of you are familiar with, which is the TBC. And the other is the automotive cylinder bore, which I spent the last week, learning a lot about, and through a lot of my friends in the industry who gave me information. And I hope to impress upon you how challenging and incredible that implementation was, and what a huge success it is. We don't actually talk about it much. So you go back to the TBCs, it actually dates back even before the 60s, right? So the moon program, obviously in the US, really drove home this need for these high temperature material, insulative materials. And if you look at, I gave you the example of lime stabilized, magnesia stabilized, and all of that stuff. The idea of yttria stabilized zirconia as a success was experimentally identified in the 1970s. And I'll go through that in a second. That led to the adoption of the technology in the aerospace, and successively followed with much more possibilities in the land-based turbines. A lot of attempts at hydrogen, even in the early part of the 2010. This slide is a little bit old. Obviously, this thing continues. It's still a successful market. But, would you ask people, is it truly a primer line coating? People hedge their bet. That means that they don't completely rely on the coating as something that would be part of the system. So basically, the components are still designed with the coating as though it's not exactly there, but it still provides benefit. Landing gear, Christian talked about, more recent, and actually there is some really nice history to this. When Lufthansa attempted to do this, and Boeing gave them permission about replacing chrome, and that led to sort of many, many years of work before it finally went on the platform for the 787. Along the way, there was another very large attempt, particularly by Caterpillar, to do replace electroplated hard chrome on a lot of their hydraulic components. And they didn't come from the point of view of chrome replacement from environmental. They actually came because a lot of their components were used all over the world, and they simply couldn't ship them back. And there was not enough chrome plate capacity. So they were looking for a local alternative to fix and repair and remanufacture their systems. And that's how they went after HVOF. So this industry ended up using WC cobalt chrome, which is still an enigma why somebody chose that. But the other industry ended up using mostly chrome carbide, nickel chrome in that applications. Now, I use the word kicking and screaming. There are two sort of important things that that may have resulted in this. In Lufthansa's case, they probably just started it because of some local aspects. But in the early years, this tungsten carbide application went forward simply because there's a lot of US government and European emphasis on environmental controls over hexavalent chrome. But if you go back now and you look, some of the new aero platforms have actually gone back to chrome plate. Why? Because you can do much cleaner chrome plate, and this is something all of us have to be aware of. You can't just simply sit there and expect that your competition is not going to sit idle. And second thing is, it turned out it wasn't the thermal spray that was expensive and difficult here. It was the grinding of the landing gear after it's deposited. So basically, you're trying to solve one problem and you created another problem. And so one needs to be careful about why these things take such, these decade-long excursions to do that. So thermal spray is being peppered with what I call inventions, but they've taken enormous amount of time to implement all of them. And you can see my list over here of all of the ideas that has come and gone. Obviously, if you go and buy a new plasma spray system, it looks really fancy, but they're really control innovations that other industries did, and thermal spray just used it. It's not technically a thermal spray innovation. So along the way, many applications came along. This Siemens fuel cell goes back 40 years. Thick thermal barrier goes back 40 years. A lot of these come and go. This technology I'll talk a little bit about goes back and also about 35 years. So you can start to think about, all the things that have come and gone in our lives that never made it all the way. So this is what got me into this whole game of trying to understand, why things take so long, and sort of what are the impediments, and how do you add value of your research to the market or the application. Ultimately, we have to realize that thermal spray is still an applied field. Even though there is some really cool science to do, it cannot stand fundamentally on its own. And that was a challenge that Professor Herman, Chris, and I faced 30 years ago, 25 years ago, when we were trying to sell the idea that we had to be an NSF center. NSF believes primarily in fundamental research. But we used some nuances about how materials are coming from extreme environments, and that has its own sort of a domain for fundamental research one needs to consider. So let's talk first about what we mean by the word innovation, right? So innovation is not simply an invention. It is inventiveness that is put to use, which means if people don't use an idea, then it's not innovation. It's still an invention. So if you take inventions, you can play around with ideas as long as you want, but to take that idea and make it adopted by the community, this second phase or the second leg of this operation is where that 20, 30 years are taking place. So, invention without innovation is basically a hobby, right? It's wonderful. We can do research and come up with it. And of course, the other problem that we all face is that, every time somebody has an idea, first, the thing is it's impossible. Then once you show some proof of concept, then it's possible, not worth doing. And then once everybody believes that it's working, then of course it's a great idea, right? And so one really needs to understand the practice of innovation along with invention if you want to see your idea go all the way forward. So most innovations are captured in this concept called the technology S-curve. You start with an idea, you make it work properly, improve, reduce cost, and then you make, so if you plot something like a dollar against time, this is the kind of agenda you will see in the systems. So we go back to our curve, and this is our technology S-curve. It started small, it had this really sharp rise, and then it starts to plateau over a period of time. And along the way, you can benchmark key innovations or inventions that became innovations that came along, right? These are identifying only these little processes. But if you look at the time to market, HVOF was surprisingly fast. It only took about 5 to 10 years to get to market. All of these other things, the cold spray, the cascaded torch, HVAF, these things have taken a very, very long time. And even the SPS and SPPS is going back, a long time. In fact, I think Chris and Herb did some of the early work in the late 90s and early 90s to even get this started. And Rich Neiser did superconducting materials using suspension in the late 80s. And so let's talk a little bit, plot the technology S-curve. So you obviously want a y-axis and you want x-axis in the form of time. And how you pick these y-axes depends on the particular system. So I'm going to give you 2 examples. One is pretty much real data, which is how many pounds per year, or can change it to kilograms per year, of YSZ or some TBC material that gets plasma sprayed. And that number is approximately 2 million per year. So about 2 million pounds of zirconia gets plasma sprayed every year for TBC applications. And if you think about it, that is actually quite a large number, given the fact that the volume of material is relatively small in this application. So you're depositing, relatively small amount. And don't forget, these DEs may be, the deposit efficiency may be 50%, the target efficiency may be 20%, even 10% or 20% lower than that for certain applications. Of course, in big drums, you can have very high target and deposit efficiency. In others, you can be much smaller, like a blade. And you're wasting, of course, a lot of materials that came along. And you look at sort of some key milestone. This is a dotted line because we don't exactly know how this line moved, I have data from here, we know where it started, and you start to make some pretty good guesses, particularly 1990 when the engine came along. Maybe this graph was more stiffer. Along the way, lots of different variants of microstructures have come along. We started with porous, then came the dense vertically cracked. Then we started to introduce some of these multi-layers. And if you look in the future, and let's go back and ask the question, why did they need this? So, you can see these pictures that are available. This one's of course EBPVD from O.A. Schultz, but there is a system need. As you increase the temperature capability, you get better thermodynamic efficiencies. And if you look at the underlying alloy over the last 50 years, the temperature capability has gone up by 100 degrees. With the addition of cooling, TBCs, and eventually EBCs, we're now getting almost a 500-degree increase in operational temperature. So that's the driver that gives you this huge boost why people want to do this. Now, just some statistics, a 1% increase in efficiency of a 300 megawatt combined cycle plant can provide up to 4 million in fuel savings and 25,000 tons in CO2 reduction. That's 1%. So we're shooting for 10% here. And so these are pretty big numbers. And secondly, by putting the TBC on, it allows you to reuse your substrate after an overhaul period. That's another huge advantage. This is another very cool slide that Mike Maloney, our colleague, formerly retired from Pratt & Whitney, shared this with me, that the heat transfer that goes through a single turbine blade is equivalent to supplying 18 homes with electricity. When you put a TBC on, you basically get 6 homes for free. That means you reduce that heat transfer, you allow the system to operate harder, and you get this essentially big. So you can see the drivers are very, very big, and the drivers for obviously EBCs is even bigger in the future. But success creates new problems, right? CMAS is the resultant of these high temperatures that we are introducing in the engine. But I'm not going to spend too much detail on that, but we got incredibly lucky with YSE, right? First, this is a metastable phase diagram that shows that T prime is not shown in the traditional phase diagram. It only comes because of certain nuances in the processing. And T prime actually has a toughness that's about 10 times higher than traditional zirconia, which is unusual. And that combination made this a very interesting material. Then, of course, we spray these coatings with porosity and layers that reduces the intrinsically low conductivity by a significant amount, by a factor of 2. And so you've got another parameter. These coatings, because of the porosities in the cracks, they're thermostructurally compliant, which means that allows them to participate with a metallic alloy, which has a higher expansion at these temperatures. And lastly, both YSE and yttrium zirconia are easily manufacturable. They have similar vapor pressure, which is incredibly lucky. That makes it easier to process. Zirconia is abundantly available, so the cost is low. So if you don't have all of these things coming together, it's very hard to convince somebody to do the applications. So where are we with this? There's a lot of interest in trying new processes and new architectures and composition. Time will tell whether this is going to move forward. These things with SPS and PSPVD have been tested for a very long time, and there are reasons why it doesn't work that easily. GE is obviously committed to EBC and CMCs. They put it on one component, more components are coming along. So that's another opportunity for our community. Let me talk a little bit about the cylinder board, which I think is an unsung hero. And I've been involved in this since 1988. So it's a long time. So if you go back, and I'm going to show numbers which are approximate, these may be underestimates, but roughly a few million bores get sprayed today all over the world. Now compare that to the TBC, which is in the tens of thousands compared to this number. So this is a pretty impressive high volume manufacturing applications. So how did it start? I showed that picture early on. There was a Japanese patent on sprayed engine liners. What really motivated was in the 1980s, there was a lot of interest in making aluminum blocks. Aluminum blocks needed a cast iron sleeve to allow them to successfully be used in a thing in a wear situation, because aluminum is not intrinsically wear resistant. And that led to this GM's interest in finding a process. But they realized early on that they cannot use traditional thermal spray, where the part rotates and the torch is stationary. So Martin Kramer, who is still involved in the field, I remember at the 1988 thermal spray conference, started asking everybody, can you guys, thermal spray guys, make a torch that spins? And the first reaction, go back to my comment about the clock, is it's impossible, right? And you would not believe, in 3 years, there were 4 rotating four rotating thermal spray torches that were demonstrated. And the part one is this, the one I have a picture of. This is a rotating HVOF. And this is how it works. It goes into a 3-inch bore and sprays a coating and basically demonstrates that. So Metco first started with the rotating HVOF. TAFA came up with the rotating air cap arc spray. Our friends Keith Kowalski and Dan Morantz in Long Island developed plasma transfer wire arc. Some of the earlier work was actually done here on campus. And then Sulzer, Gerard Barbizot, demonstrated the idea of actually rotating a plasma torch inside a 3-inch bore. So you can see how incredible these innovations are. This is not easy to do. And so what that led to was GM and sorry, I'll close that. So GM and Ford put enormous amount of effort to try. Ford followed GM, and they've put enormous amount of effort into it. GM chose HVOF, Ford chose PCWA, and through the entire 1990s, a lot of activity went on in the US, and some of us were part of it. Along the same time, VW started to engage plasma, and they started to develop these engine block applications. BMW and Mercedes were somewhat quiet, but in 2010, they basically launched a mass production line to deposit spray bore. This is called spray bore inside one of their commercial aluminum engines. And that took off. And this number, you can see how steep this graph is, and it has been phenomenal what it is. But one has to be cognizant as to what's coming. So more recently, Ford is restarted. GM is no longer pursuing it, but Ford and Nissan, working with Flame Spray Industries, have introduced this into lots of different platforms. The most notable high volume is the Ford 150 truck. And Keith mentioned that they themselves have done about 8 million bores since 2018. And a peak is predicted around 2027, largely because of the electrification of the automotive. But those of you who have not seen this evolution, and I'm framing it in the context of this innovation chart, you can see how humbling this is. And look at the time here. This picture is from the 50s. The early work started in the 80s, and we are talking at high volume, really took the last decade to get there. So why did we need it? Again, go drive the system needs. And this is from Martin. So basically, this is how you will shrink fit a cast iron liner into aluminum block. Obviously, thermal spray is much easier. You prep the surface, spray, you hone, and you're done with it. And there are many advantages. You get a weight reduction because you don't use this thick cast iron area. You get what we call packaging and downsizing. So if you put a liner, the gap between these engine blocks have to be quite large. That means the whole engine becomes bigger. The moment you make the engine become bigger, you have to make the car bigger. And these people are struggling to get as much space out of this. If you open a hood of a modern car, you can see there's no place to even put your hand in. It reduces cost relatively, but other really impressive advantages by having a thin coating was it reduced the heat transfer. Nissan published the 20 to 50 degrees C heat reduction. And then there was tribological improvements. And it turns out the porosity is a virtue here because you can trap small amounts of lubricants inside it. But there was an enormous amount of challenges to meet this. First, you needed a rotating torch operating 3-inch. You need high speed, right? Because you're trying to do 24/7 operation without stopping. You want high throughput. You're not going to go back and forth. You just do one pass and move on. There's no chance to do any human touch, no soft masking. You need cheap materials. Coat hanger wire is what they used, mostly steel. You don't want to do grid blasting. This is something I'll come to in a second. And then on the side, you need automation, consistency, you need to apply it worldwide, you need to be predictable performance because you can't have a block fail in a fleet, and market acceptance. So, it is just, when you just think about this, it's a really amazing accomplishment. This is a picture of an actual block, and you can see how these pores can actually potentially help you in the applications. Lots of success stories. This is the one that went into production in 1998. This is the first known production car. Then, of course, the BMW and Mercedes, lots of special cars, Bugatti, Nissan, Ford Shelby Mustang. This is the one there's actually, the Ford actually advertises this. And then, of course, the applications. Now, along the way, lots of innovations that are not thermal spray that came to being that actually helped this application. Unfortunately, I don't know why this in my copper, but this is one of the important applications came from on how to prep the surface. This is a method and apparatus for application of engine blocks, and then how to prep the surface. So I already told you the rotating start torches that came in those days. There was a lot of effort to get rid of grid blasting. GM and Progressive Technologies came up with water jet surface preparation. Ford used a fluxing concept. And there was a lot of really great technology that came from Germany on laser preparation and machine tool. Ultimately, the winner is this machine tool concept. So you can mechanically roughen using a tool block that allows you to create these featured surfaces. And that prevents the use of grit. The automotive industry is already used to using machining, and that made this a huge advantage. Lastly, high-speed honing. I mean, you don't want to go and machine this. This thing gets done literally in 30 seconds, right? So bore every 30 seconds, mechanical roughening, non-stop production. That means you're not turning off the torch pretty much all day. So how do you account for that? And many times, multiple torches are spraying these blocks. So one example is 3 followed by 2 to do a 5-cylinder. If you're doing 6-cylinder, you do, I don't remember how they do that. But so you can see that this is an incredible example of invention becoming an innovation, but look at the time that it took to get here. Now, I want to finish with a few points relative to sort of why we're doing. I know I'm running a little bit late. I hope Saurabh, you won't mind. First is, let's compare TBC with spray bore. So TBC is low volume, low throughput, high cost. Spray bore is high volume, high throughput, high cost. They're exactly the opposite ends of the spectrum. Destabilized zirconia is a complex T-prime metastable material. Here we use steel. It is metastable because it becomes tight, but it's relatively simple. Lots of requirements, relatively fewer requirements, multiple facilities, multiple components, lot of time temperature dependencies. None of that occurs over here. However, there's a big difference. A lot of TBCs are materials driven. A lot of spray bore was manufacturing driven, which means what ended up happening, if you look at this industry, very few of us thermal sprayers are involved. It's really done at the automotive and then automotive integrators that do that. That's why we don't hear about them. Let me kind of go through for future. There's all these ideas about cold spray, suspension spray, high entropy materials, nano. Always remember, these things take a long time. This is cold spray, and I'm not going to belabor that. It took a really long time to catch on. And sometimes, many times, you'll wait for the patents to expire before these things take off. And a lot of the focus is on small volume, special DoD applications. I just recently gave a talk, and I just summarized sort of my own history in cold spray. So we developed a cold spray printing in the 2000s for our sensors program from DARPA, worked on property measurements, residual stress measurement going back 10 years, doing mechanical efficacy, and then, of course, the in situ measurements. So you can see that even in my career, and I'm sure Christian and Shrikant and others will say the same thing, lots of different things are constantly happening. over the years, and many times it gets revisited in our livelihood. Last few points. So what's the future? I have no idea. But clearly we are all beneficiaries of thermal spray, and we hope to see that it'll remain for another 100 years, the torch being passed on to the next generation that will hopefully carry this on. I think there are three sort of important aspects. First is you got to, of course, innovate, which means not just invent, take it all the way through. You got to integrate. Don't try to do everything yourself. You're much better off collaboration, and these kinds of schemes that Sarah and Alan are putting together is appropriate, because that's how you allow the world to know. In fact, I think Christian might remember that I think 20 years ago, I led a proposal called International Thermal Spray Institute to National Science Foundation with 18 countries. Unfortunately, it was rejected, even though we ranked well. But there is a really great opportunity to collaborate and partner. Past is prelude. I want you to know that there were really smart people who took a lot of risks in the 50s and 60s. So any sufficiently advanced technologies in this industry was magic. Can you imagine working with a hand-sprayed plasma torch in the 1950s and 1960s? There's a lot of technology came in the 70s and 80s. And of course, I think we're, as Christian pointed out, we're entering this big knowledge era where we're trying to connect the two together. Personal observation, there's a lot of experience and tribal knowledge in this area. And as we started to put more knowledge, we became more fearful. As my former colleague from DARPA said, the more stupid you are, the less fear you have, the more risk you take, the richer you'll get. I'm not advocating that, but something for you to think about. Second, thermal spray is gee whiz. And one high school student called it, it's so hard at school here. But that doesn't mean it's a universal solution to a problem. It's only a tool in the toolkit. An OEM will choose the proper tool to meet their application. If suspension spray is great, but it's expensive, they may not choose it. Same as cold spray, right? And you look at the cylinder bore, what it took to get there. And many times there's a disconnect between what we do in the process side and what the system really needs. And this is something one needs to accept. And I'll skip this innovation risk, but let me talk about sort of the fact that what I mean by system-driven and market-driven. I'll go through this quickly. So when a market needs it, like the cylinder bore or the TBC, they drive the product. And we are somewhere in this loop. If you're trying to do research, coming up with new disruptive ideas, suspension spray, whatever, then you have to go through this applied research to convincing people for technology adaptation. And most technologies fall in this, what we refer to as the valley of death. So if you look at the hurdles one has to overcome, this process coming bottom up can take a lifetime. Same with the other one, right? Both of them take pretty much an entire lifetime to get to. TBC and spray bore reflects the top part, cold spray SPS. We're still in this. Are we going to get across this bridge? We don't know. And that'll tell us how it's going to go. So where do we go here from here? Remember that the system is the driver if you want to make an application. And the science comes at the bottom, right? And so whatever we do in fundamental knowledge has to meet some common technology requirement because we are a platform, and that has to lead to the market driver. So there's a lot here that one has to take into account. It's a lifetime of working. So you can think about these in these constructive ways. You got system enabling innovation, but you have to kind of bridge these floors in the operational space. So I'll finish off with just a little bit of story about our, where we came from. Stony Brook had the thermal spray lab under Professor Herman in the 70s to 80s. And then we convinced National Science Foundation to invest as a center 25 years ago, actually to date. That led to a renewal. So the successive programs gave us about 15 years worth of funding. And then subsequently, we became what's called self-sustaining. Along the way, DARPA came and gave us some nice money. The university helped build a facility, and our industrial members contributed to that. We participated in lots of different areas, and I have a whole story on this. I'll come to that again. Many people went through the center. Lots of papers got written, technologies got developed. And the nice thing with our group is we've always maintained these connections. We often have our reunions, and many of our colleagues are still in the thermal spray business, which is very gratifying. The thing that we learned about 10, 15 years ago is how do you take science to practice? And that's sort of an important mission of any innovation, as I mentioned. And so we started to think about how do you come up with this agenda. So we used the term PAINT, and I skipped through that slide kind of quickly. We called it Partnership for Acceleration and Insertion of New Technology. And one of the most effective models was to build this community, which we call the Industrial Consortium. There's two missions. One is they kept the industrial support kept the center to continue to exist, because the NSF starts to cut off its budget. They're giving us $750,000 or $1 million per year, but then it starts to wane over time. Somebody else has to pick up the core cost. And we've been fortunate, there's been the fluctuations in the members, largely due to consolidation of companies and so on and so forth. But this membership has lasted 20 years. We're actually celebrating our 20th year this year. A lot of international companies. Each company pays a membership fee to the center that allows us to keep this pre-competitive partnership going on. And what we do is take these signs. This is some observation on injection, on nonlinear behavior. I won't get into the details. But then we take it and actually we demonstrated it on industrial sites. So we did industry university joint projects and doing the demonstrations. We did about 32 field trips. We stopped doing them because it just wasn't practical. We expected industry to pick that up on their own. So with that, I'll just conclude by leaving this on the screen. If anybody wants, this is a free download that essentially talks about this innovation cycle. You can just hit my name in the integrating materials and manufacturing innovation, and you should be able to see it, get it for free. This should be coming out soon. We just celebrated our 25 years, and our website should have most of the articles that you're looking for. With that, I thank you for your attention. I'm sorry I did start a little bit late, but I hope we can still have a discussion. Thank you.
Thank you so very much, Professor Sanjay Sampath. This was a splendid, an acutely combined concept of history, philosophy, entrepreneurship, thermal spray manufacturing, and then so much more beyond thermal engineering and thermodynamics as well. It was a fascinating talk, and you can see that people were already acknowledging how sincere of efforts have gone into this revisiting of history, which was really an enlightening experience for me and I'm sure for many others. So there was just this simple question from which was towards the sustainability drive. Can we just simply pick up the wasted powder and respray it?
Not easily. Many of these things are qualified, so it's very difficult to reuse things. Mostly they get reprocessed. I would say 90% of them goes into a landfill. In the ceramics, in the metals, I'm sure people extract things like carbides and things like that. We have our own problems when we have dust collector material, or whoever we give it to, they like the metals, they don't like the ceramics.
So if I ask you a couple of more questions from my end, Professor Sampath. So within the thermal spray area, as you being one of the experienced campaigner of it, where do you see, which aspect of the technology do you see holds more scope for sustainability, both in environmental terms and perhaps in material terms?
Yeah, so, and this is an area we're working on. In fact, I'm giving a talk tomorrow to the National Institute of Standards and Technologies on infrastructure, for example. As you know, US has passed this big sweeping bill on infrastructure. So I think there is a lot of opportunity for metal remanufacturing, steel, aluminum, if you look at 85% of structural materials are made out of steel, and the volume, when we talk about volumes of steel, you're talking about a single country producing 10 million tons, and we're talking about 2 million pounds. Just imagine that discrepancy. So there is a lot of opportunities for corrosion, for degradation of the alloys that don't have to be taken down. So metal remanufacturing, metal sustainability, we think is a very important future area. Now, cold spray has kind of elevated that interest, but if you really go back and look at the applications, pretty much most thermal spray technologies can do this. Arc spray is very popular because it's cheap. You can build up quite a bit of structure. HVF is excellent, in many cases actually better than cold spray in terms of the quality of the deposit that you can make. And of course, cold spray has its own niche. So I think there is a real opportunities. The US Department of Energy has a program called Remade. They're trying to get involved in this. We were involved with the Remanufacturing Industries Association. So I think the idea of another part is the coating can give you a platform for remanufacturing. That is, if I have a structure and I don't want to lose the structural capability, add a coating to it, let the coating take the beating. When the coating is gone through its life, you take it apart, put another coating, and restart it. That's what people like Caterpillar do, right, with their really harsh environment components. So to me, that's a big area for future interest. Functional ceramics is a possibility. The aerospace, you don't have to tell them, they'll drive it, energy systems. But I think they're still limited. We ought to make the pie bigger rather than trying to, let's say it's a suspension spray. You're just going to replace some of the existing technologies. So we have to think about opening up these opportunities.
Excellent. Perhaps one more thing I could probably add to that is there's a lot of drive, I'm sure in the US also, but particularly here in the UK, is about towards net zero manufacturing. In that footing, how would you see that thermal spray can go towards that direction?
Yeah, I mean, obviously, if you use an electrical process and if you can generate the electric somehow, net zero, so plasma spray is obviously quite a nice and attractive agenda in that area. I would say that, we are so small in that landscape that I think our ability to impact things at such a big level, even if you take a large manufacturing operation, even like the automotive, the actual thermal spray part is incredibly small, right, compared to everything. So I think it'll be hard to capture people's attention on that domain quickly, but that doesn't mean that we ought not to figure out how to make better target efficiencies, better deposit efficiencies, increasing life of components, use less material. So there's always great advantages to continuously innovate, because that's called efficiency innovation. So any efficiency innovations is easier to implement than disruptive innovation.
Sure. One question from the audience, Sanjay, is could you please give some examples for landing gear related parts where thermal spray coating is used and the purpose is to increase corrosion resistance or wear resistance?
Yeah, so the landing gear is, as I mentioned, 787, even some 737s are all thermal sprayed, and it's not because of corrosion. It was mainly an environmental driver. Basically, there was a big effort to get rid of chrome plating because chrome plating generated hexavalent chrome, and it was not good for people's health and well-being. And that was a driver, particularly from US DOD and also from the major manufacturers. But as I mentioned, the chrome platers have become much smarter, and so they're coming back. I think thermal spray coatings are better in some respects, but they're also more expensive because you have to grind them, and chrome plate is that way a lot cheaper. So you'll always find these competitions where what you think is your technology advantage comes back with some other innovations from the other. So we have to constantly fight because the system doesn't care what technology it uses as long as it meets the criteria. Yes, Gustavo.
Thanks. A very interesting talk. So I have a question about the portability in terms of you were saying remanufacturing, and I would go further into maintenance. How portable can be the technology so that you can envision thermal sprays for local healing, if you want, or local maintenance, let's say in an airport or in a facility that is not specifically designed for this?
Yeah, I mean, it is a very portable technology, not so much in aerospace, because there's a lot of considerations in aerospace in terms of regulatory. But, I showed that example from the 1950s or 1960s about the paper industry. That's still being done today. People still take a truck with all the thermal spray equipment, drive to a paper mill and coat the paper mill. So it is fundamentally possible to do this. In fact, the thing we're trying to do with infrastructure relates to that. There's a lot of aluminum cold spray repair, which is handheld, and you go and fix parts with your hands. Again, limited in terms of capability, but fundamentally, there's no reason why thermal spray is not portable.
Thank you. Very interesting.
Okay, Professor Sampath, I think there is no more question left to answer. So I think in the interest of time, we can close today's session. And it was fascinating to cover the Western viewpoint on the exciting technology of thermal spray. And tomorrow we have a lot more coming from East, especially from Australia, India, and Dubai. And I would like to now begin to invite Alan to say final remarks for today before we close the session for today.
Yeah, I'll just thank the two speakers again. So I have really excellent talks. One question that came to my mind, if you don't mind me just asking, all that work went into the cylinder bore coating technology. And in a way, it's a shame that's going to be not used so much as we move away from the internal combustion engine. I just wondered, can you foresee any applications for that technology in areas other than cylinder bore coating, since all that work went into coating cylinder bores? I just wondered if there are any other applications for that technology.
Yeah, it's a good question. Not at the volumes that we're used to. We've tried to work with Metco on ID landing gear, and there are obviously applications, but many of those things you can rotate the part. You don't need to rotate the cartridge. Mm-hmm. So this idea of doing something for 3 inches, rotating these things, it is so specific to that application that it's very hard to. But that's why I said it's a manufacturing technology. It's not really a materials technology. So that means you're dedicating it to manufacturing. I would say that you never know. Right, there may be some battery applications that'll come along and it'll be perfect for it. And I hope that there'll be gearboxes and wind turbines. You typically cannot do long shafts with these things. So these are limited. This works really well because it's short, because they go in and out very quickly. But you start going deeper, then you get all this turbulence coming your way, and so it's not easy to do. So I think the fact that it exists is wonderful. I don't know whether the wire guys probably don't have that much versatility, but I suspect the powder people have a lot more opportunity to look at other solutions, because they can spray ceramics, which wires cannot do.
Yeah. Okay, thanks very much, Sanjay, and thank you very much to Christian as well. Both really excellent talks. Swarov's telling everybody to submit the papers, the special issue. I probably should say that we've really enjoyed putting this together for thermal spray. So we are going to repeat the idea for other technologies in the future, probably one on electrodeposition. That might be in October, November time. And we might do one on PVD. So if you think it's a good idea, which I think it has been, then we'll repeat them. But of course, for the remainder of this week, we've got some more very interesting talks on thermal spray methods, and hope to see you there.